In Smith chart, you can see that wavelength towards generator and wavelength towards load. So in this video, we are going to see what is meant by wavelength towards the generator. So let's see. So if we consider a RF circuit system, it will be having a source. We can also call it as the generator, which is connected to the load through the transmission line. So this source may be like maybe IC, or it can be like some transmitter system. The load will be usually antenna. That is, the load is connected to the source through the transmission line. To analyze what is meant by moving towards source or generator, let's split the circuit into two sections where we can have the source and we have the load which is connected through the transmission line. So, if we see the input impedance of this system, that is the load connected to the transmission line. So, in actual cases, the antenna connected through the transmission line will be having an input impedance which can be given by the expression Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L, where this Z0 is the characteristic impedance of the transmission line, L is the length of the transmission line, and beta is given by the expression 2 pi by lambda. ZL is the load impedance, and Zin is the input impedance that is seen by the source due to this load is connected to the transmission line. Here you can see that the length of the transmission line has an impact on determining the input impedance. So moving towards the source or generator means that what is the impedance of the load that is seen from the source when it is connected through a transmission line. That is meant by moving towards the source. So what is the impedance of the load that is seen by the source when it is connected through some transmission line? That is meant by moving towards the source. So let's see. First of all, we know that when we are designing an antenna, our main purpose is to make the antenna impedance same as the characteristic impedance. So if we have the transmission line impedance is at 0 equal to 50 ohm, we will try to design the antenna having the impedance same as 50 ohm. That is the main purpose. So let's see what will happen if our antenna impedance is same as 50 ohm. So we know that this is the input impedance calculation equation. Here we can see that when the load impedance is same as the characteristic impedance, the equation will be transformed like this. So it is like Z0 into Z0 plus J Z0 tan beta L divided by Z0 plus J Z0 tan beta L, because we are considering ZL equal to 0. That means that the input impedance will be always be equal to the characteristic impedance Z0 or ZL. So if the load impedance and the characteristic impedance are the same, the input impedance will always be a constant irrespective of the length of the transmission line. So whatever be the length, the input impedance will always be the load impedance or the characteristic impedance. So that means that if our antenna is matched completely to the characteristic impedance is at 0, whatever be the length of the transmission line, the input impedance will be the same. So this system will act as a perfect system. That is why it is so. If the load impedance is same as the characteristic impedance, the source will see the same impedance irrespective of the length of the transmission line. So let's now consider the case where the load impedance is not equal to the characteristic impedance. So in that case, based on this equation, we can see that the input impedance will be having an impact on length of the transmission line. So with respect to the length of the transmission line, the input impedance seen by the source will be changing. So let's see more into that. So let's consider the system where we having the source impedance and we have the load which is connected to the source through a transmission line having the length lambda by 8. So in that case, we are considering the characteristic impedance is 50 ohm, and for I am going to consider the load impedance as 0 ohm. So I am considering 0 ohm or short circuit as the for our easy explanation. This is not just like a practical case, but for the easy explanation, I'm going to consider ZL equal to 0 ohm. So let's see what will be the input impedance seen in this system when the transmission line length is lambda by 8. So if I want to calculate that, I have to substitute everything in this equation. So this is our equation, Zn equal to Z0 into whole things. So I know that the load impedance is 0 ohm, that is short, and length of the transmission line is lambda by 8. So after substituting everything and making all these complex calculations, we will get the input impedance as Z0 into G. So this is the input impedance that is seen in this system. So in this Smith chart, we are always seeing the normalized impedance. So I am just normalizing this value to see what will be the impedance seen by the system. So that means that the input impedance seen by the system is just J. J means 1J, or it is the inductor. So if I am not going to use the Smith chart, if I want to see the input impedance of this system, I have to make whole lot of calculations. But let's see what will happen if I am going to just use the Smith chart. Okay. So this is the Smith chart. Here I know that the load impedance is at 0. That means that is at 0. This is the impedance, that is the short. This is my load impedance, and I have to see what is the input impedance if it is moving towards the source, or source is also known as generator. Here you can see one circle showing wavelength towards the generator. So this wavelength corresponds to length of the transmission line. So the length of the transmission line that we are considering here is lambda by 8, which is 0.125 lambda. So if I want to see the input impedance, I have to just trace through this length. Like it is 0 here, so I have to go to 0.125. That is the length of the transmission line. So it is like 0.04, 0.05, 0.06, 0.9, 0.1, 0.125 will come here. This is 0.122, 124, 125 will be coming here. So it will be the midpoint. So what I have to do is I have to mark a line from this to this point. I'm not sure if I can draw a straight line, but it will be, oh, sorry. I draw a straight line, and so this is intersecting at this point. So this is my short, and this is the outer circle. So if I trace that and this point, we can see that this is the intersecting point. That intersecting point shows 1. So this is this line, that inductance line. So inductance line is overlapping with this line. So this has a value of 1. That means that this value is J. So we got J as the input impedance. So this is the same as whatever value we have, sorry, whatever value we have calculated using these complex calculations. So with using Smith chart, it is very easy to calculate what is the input impedance. Instead of, we don't have to use all these calculations, we just have to trace what is the length of the transmission line along this path and it is very easy to see what is the input impedance. That is the importance of Smith chart, and what is meant by wavelength towards the generator. So let's analyze this using some more examples. So I'm going to consider the load impedance and the input impedance which is seen by the load. So let's see what will happen if I'm going to connect the load impedance through a transmission line having length of lambda by 8. So it will produce a impedance of J is at 0, and if I'm going to add another lambda by 8, it will be lambda by 4, so the input impedance is infinity, and another lambda by 8, then the input impedance is minus J is at 0. So if I am going to add the transmission line like this, every time I may have to do the complex calculations, but using the Smith chart, it is very easy to trace what is the input impedance using this curve. So so I have tabulated everything here, like to show what is the impact of the length of the transmission line. So here you can see that by changing the length of the transmission line, even the load impedance is always short. You can see the change in the input impedance. So here you can see that when you are connecting the load to a quarter transformer, you can see that the impedance will be reversed. The short will become open circuit. And when the length of the transmission line is half wavelength, you can see that the impedance seen at the Z will be the same as whatever be the load impedance. So this is just tabulated for the calculations. If I want to use the Smith chart for the same purpose, it is very easy. So now I know that this is my load impedance, and if I have to find what is the input impedance, if I am going to connect that load impedance through a quarter transmission line. So I have a short load here, and I am going to connect that to a transmission line of length lambda by 4. What will be the input impedance? If I want to see that, I just have to move through along this path, wavelength towards the generator. So I'm going to consider this case lambda by 4. Lambda by 4 means 0.25 lambda. So I'm going to trace wavelength towards generator, and when it is 0.25 lambda, here you can see that it will be along this line, and the outer curve and this will be intersecting at this point, which will correspond to an impedance of infinity. That is how we can calculate the input impedance, that is wavelength towards the generator. So here you can see that if you trace along this path, like this one, if you are going to trace along this path, that is from 0, like it is 0.25 here, and 0.36, zero point 0.4, it will end 0.48, 0.49, zero point 0.5. So the complete circle of this wavelength towards generator is half wavelength. So it will start from 0 and it end at 0.05, sorry, zero point 0.5. So the complete rotation is 0.5 lambda. So let's see if I have to extend the length of the transmission line like 0.625 lambda. So here you can see that it is more than one full circle. So in that case, what you can do is 0.625 lambda is 0.5 lambda plus 0.125 lambda. So it is like if you extend one more time through that circle, you will get that answer. So you don't have to worry, even if the length of the transmission line is more than 0.5 lambda, you can uh, move through one circle, then again what is the remaining you can move, then you can find out. So here let's find out what will be the input impedance if the length of the transmission line is 0.625 lambda. So we will start from here and we move the complete circle. So we completed zero point 0.5 lambda and the remaining is 0.125 lambda. So we will go again and here is the value 0.125 lambda, and if we draw a line through this, it will extend at this point and we will get that impedance as J. That is how we are calculating the input impedance when we are moving towards lambda. So now you have seen what is the importance of wavelength towards generator. So first we have considered a very simple case like ZL equal to 0. Now let's see what will happen if we have to consider load impedance like a complex value. So the question will be like, what will be the input impedance if the load impedance is 50 plus 50J and length of the transmission line is zero point 0.3 lambda. So you have to calculate the input impedance if the load impedance is a complex. And you have given the characteristic impedance as 50 ohm. So when you are dealing with the Smith chart, first of all, what you have to do is whatever be the impedance you have given, it has to be normalized. So you get ZL as 50 plus J50. So first step is normalize this impedance. Normalize means ZL divided by Z0. Then you will get the value as 1 plus 1J. So this is the first step, and next step is find out this point on the Smith chart. So now we, sorry, now, so, so now we know that 1 is the resistance and 1J is the corresponding, the reactance of the load. So if you want to mark this point, what you have to do is you have to find the 1 in constant resistance circle. So this is the constant resistance circle, and you have to find 1 in the reactance. So here you can see that these lines are corresponding to the inductors, and this is the one, this one is for the inductor. So if you find that intersecting point, that will be corresponding to 1 plus 1J. So mark that point. And next step is extend a line from this matched position. So one is the matched position and this is our identified line, and draw a straight line from here through this line and extend so that it will touch on the wavelength towards the generator line. And here you can see one value because this point is 0.162 lambda. So this is the corresponding wavelength for this load impedance. So you have to note this value. So this is the second step. Second step is find out the wavelength corresponding to this load. So after finding out this uh, wavelength, so this wavelength is like from 0, this is intersecting at this point, that is 0.162 lambda. So when you find out that wavelength, what you have to do is you have to add this wavelength to the wavelength in the question, that is zero point 0.3 lambda. So now our purpose is we know that, so we have the load impedance. So we have find out what is the wavelength corresponding to this load impedance. Now what we have to do is we have to connect the transmission line having length of zero point 0.3 lambda. So we have to add this and this together. That is the next step. So when you add that, you get 0.462 lambda. So that is the total length towards the source. So your aim is to find the input impedance at a length of 0.462 lambda. So now what you have to do is you have to find this 0.462 lambda on these wavelength towards generator line. So let's see that. So my aim is to find 0.462 lambda. So here you know that this is 0.25 and move along the outer circle and go for 0.462. So this is 0.45, 0.46, 0.462. So now you got the point of that wavelength. Next, what you have to do is you have to draw a line from here to this matched point. So this matched point is always our reference. So I draw line from here to this line. So that is, I have drawn a line from 0.462 to this point. So next step is we have to draw a circle with center this point and radius as this point. So if you draw a circle, you can see that this circle and this line will intersect at a point. So this is your desired input impedance. So this is the input impedance that will be seen when we are connecting a load of 50 plus 50J to a transmission line of length 0.3 lambda. So from here to here, it is like 0.3. So you got your input impedance. So this is how you can calculate the input impedance. So here that point will be around minus point, sorry, 0.4. So this is the constant resistance circle. You can see it is intersecting at 0.4 and this is the reactance, it is for 0.2. As it is on the below line, it is for the capacitance, that is it is 0.4 minus 0.2J. So this value will be your input impedance. So if you multiply that by 50, you will get your input impedance as 20 minus 10.5J. So this is the steps to calculate the input impedance if you have a complex load connected to the transmission line. Okay. So I have just noted down the steps that you have to follow. So if you have given a complex impedance, first of all, mark that impedance and then draw a line from here to that point and note the note the wavelength there. Then add the wavelength given here, that is 0.3, and find out that point. So in effect, you are just extending from here to here as 0.3 lambda. So from here to here, you will be extending 0.3 lambda to get the impedance. So now you have the input impedance here. So these are the steps that you have to be followed to find out the impedance at the input if you have connected a load impedance. That is mean by wavelength towards the generator or wavelength towards the source. So in next video we can see what is mean by moving towards the load or wavelength towards the load. Here you can see that the counterclockwise rotation. So in our next video we can analyze that. So moving towards the source actually means that the clockwise rotation. So I hope you get some idea about what is mean by moving towards the generator. Thank you.